Hello, everyone. Welcome to Automation and Security in a Cloud DevOps World. My name is Phil Christensen from Logicworks. I've been a senior solutions architect at Logicworks for 3 years now, and I've built a lot of the automation tooling that we use. I'm looking forward to going through this presentation with you. So just a little bit about Logicworks. We're a managed service provider that designs, builds, automates, and manages enterprise AWS clouds. This basically means that we can be an extension of someone's DevOps organization, and we can help them with various parts of the process of either migrating to the cloud, automating an existing cloud solution, or expanding and using more advanced technologies as well. So the days when IT managed a monolithic and infrequently modified system are long gone. We're moving into a new world where developers expect efficient systems where they allows them to update and deploy their. I want to start this all over again.
Go ahead. I can just edit it. Totally problem.
I figure I'll start from this slide, though.
Sure. You got it.
The days when an IT department can manage just a single monolithic and frequently modified system is long gone. These days, IT engineers need to be far more agile when dealing with the needs of contemporary IT practices, particularly developers who are leveraging some of the new technologies that are only available in the cloud. The question that we have to answer for ourselves is, how do we manage efficiently an environment that is under constant change? We want to make sure that not only are we adhering to best practices as we go forward, but that we can appropriately make changes and have the operational concerns covered as we go forward. And the key to this is automation. Now, there's a lot of this presentation is really going to go through the old world way of doing things and the way things are in the AWS cloud or in the modern cloud environment. And so there's a lot of different things that sort of been happening in tandem as this move to the cloud is underway. But in the old world, we're used to the limitations and the requirements for improving infrastructure are always based around throwing money and people at particular scale problems. Either you're going to buy more hardware, you're going to hire more engineers, or you're going to implement more complex processes that then take away time from your engineers, thus making them less efficient. So the solution to most of these things is to really develop smarter software to control the infrastructure that you deploy, and this is particularly useful when you're in a cloud environment. Now, when we think about DevOps in the cloud, we largely base this around 4 major principles. First of all, that we're going to design for constant change. We have to acknowledge the fact that in the cloud environment, the expectation is there that not only are there new features and new services being introduced all the time, but the expectation from developers and systems people is that they can continuously make updates, continuously pushing new improvements to their environments and doing so quickly and effectively. And so that requires a rethinking of the way many IT providers handle supporting the users that they work with. The second principle we're going to follow is the idea of building repeatable components and not individual little snowflakes. Sometimes this is called the pets versus cattle mentality, or just thinking about really leveraging the services you're creating in a way that lets you use these things over and over without repeating work. The third principle that we follow is possibly one of the strongest ones, and that's that we plan for failure in every deployment. We recognize the fact that in any given architecture, we always know there's going to be some chance of failure. But when we're in a dynamic cloud environment, it's a little bit more crucial that we specifically go through the testing and thought processes around how to best anticipate a failure scenario with something you've deployed. And finally, another crucial point is the idea that human effort is really a form of security risk. Everything you do manually, everything that you're trying to track by holding it in your head, is subject to the normal limitations of the human existence, that there's only so much you can remember to do, and it's all too easy, even for somebody who's very experienced, to forget details of a technical process. And the more we can do to automate the process and remove the human element from places where it doesn't add any additional benefit, the more we can reduce our overall security risk.
So when designing for constant change, we have to prepare for a variety of different changes. Some of the more common ones that we look at are things like whether we need to stand up a new environment. If a customer has a development environment that they've been building an application in, we have to be prepared for the fact that one day they're going to want to move that into production. Or maybe they already have a production environment and they realize that they need a more sophisticated software development lifecycle that requires them to have an independent environment for testing. We want to be prepared for that scenario. Now, another common thing that comes up for us is updates, changes to the environment that we've created, and usually this is sort of hand in hand with the desire to do so without any kind of interruption. So that meant really planning for ongoing changes. There are some things that we did with regards to how we actually choose to employ our CloudFormation stacks, different things that we followed to avoid running into the chance of failure during an unexpected update. We also have to prepare for some more trivial things like the idea of an instance failing. Now, this doesn't really happen very often at the instance level in the sense that, you know, if you deploy a virtual machine and you run it for a while without, you know, a lot of change happening on it, you can still have a back-end environment that somehow has a failure. You know, the actual hardware that instance is running on at AWS can have a failure, and that requires at least a restart of that instance, if not an entire rebuild to be sure that, you know, all of the details that go into that instance have been considered. Another common scenario is capacity planning. You know, if we really want to leverage some of the best features of the AWS cloud, we want to make sure we have the ability to scale our EC2 instances up and down as needed so that we can be reactive to the amount of actual capacity that we require. But at the end of the day, this really means continuously terminating and recreating the instances that make up this scalable group. So we really have to be prepared for that scenario, and this is where we talk a lot about instance lifetimes, that even in a scenario where a given instance may not be part of an autoscaling group or something that is prone to dynamic changes like that, we still want to have an idea of what the instance lifetime is. You know, from the moment it gets started up to the initial software being installed on it, to the ongoing changes that might happen as developers deploy to this instance, and until the actual end of that instance lifetime, either because it gets retired, because it crashes, because it gets replaced with something new. Whatever the scenario is, we have to plan for that lifetime of an instance. And then finally, and this is something I just touched on, is the idea that our developers are going to need to push code to this. So not only do we have our initial infrastructure that we deploy, but there's the ongoing changes that are put into play by our development team. And there's different ways that we can handle that, whether it's an approach that actually just updates the code in place or something that leverages some of the disposable infrastructure that we'll talk about a little bit later on. But our overall goal is basically just to maintain a known good security model without having to involve the security team in every change. So this really means ensuring that we have planned for a basic level of security in all of our templates and infrastructure shortcuts and so forth, but also that we have a way to ensure that no changes have happened to these things that we've deployed in the intervening period. So let's talk about standing up a new environment. Now, in the old manual approach, this was a very slow process. This meant that we were going to have to actually go into our account, start standing up resources, create the network, create the instances we're going to deploy into it. There may be tags that need deployed, configuration changes. We run into this scenario where every environment we deploy at least has the opportunity to be slightly different. It's possible that we might be just so focused on making sure we cover everything that we manage to get these environments relatively close together, but as long as we're doing this manually, there's always that opportunity for failure. And it means, in the end, that security and operations teams can need sometimes 2 or 3 weeks just to test new infrastructure. So if we take our more automated approach to this, we're actually leveraging as many pre-built templates as possible. At Logicworks, over time, we've generated an entire library of pre-existing CloudFormation templates that we can mix and match and combine to create a custom environment for particular users, while sort of applying the standards that we think are important to have in place that either we've discussed with the client or maybe they don't even have a position on. Part of the value of having these pre-existing templates is our ability to have a baseline set of standard security procedures, standard agents, like with regards to things like intrusion detection, log shipping, centralized authentication with some sort of Active Directory or other kind of identity provider. And basically, we can ensure a baseline level of security in a variety of ways. So we're bootstrapping this operating system with a known manifest that's been going through reviews, that's been used to be deployed many different instances across a wide variety of different clients after an extensive testing and deploy pipeline. So we basically are using the standard deploy process that's common to the software development lifecycle that we're familiar with from the software world. You know, if you have a process for adding a new environment, then that also means that you can easily do so again later on. So maybe we're thinking about it as, well, we're creating QA after we have dev, or we're creating prod after we've had QA, but in the end, we can use this process to do in-place deployment. So we can do a blue-green deployment that is safely deployed without any chance of failure, but we still can have the advantages of having all those security procedures that we had mandated need to be in place can already be baked into this template that we do, so that it again reduces the chance of human error, reduces the amount of things that we have to track in our head, and basically makes the process of deploying a new environment a far more straightforward process that can be a core part of either your deployment or testing procedures. Now, let's talk a little bit about a build process. Now, anyone who works very much with software and software development are probably familiar with the idea of a deployment pipeline. Well, this comes into play for Logicworks as well when we deploy our actual infrastructure. And this is based around the idea that a CloudFormation template is used to build VPCs and other resources according to whatever standards that we've specified, some of which we've developed over time as part of following the AWS well-operated instructions. Others are just things that we learned after periodic requests from clients and things of that nature. So once we have our initial VPC spin up, the next thing, though, is to really deal with what ends up taking a lot of the time in any infrastructure build. If you're leveraging as many of the AWS resources as possible, you can reduce the number of times you have to deal with a complex boot process for a custom EC2 instance, but it inevitably will be something you have to deal with. And in our case, we focused on the idea of having a core set of boot scripts that were going to be identical in basically every deployment. Early attempts to deploy infrastructure that has some sort of automated boot process is often based around the idea of supplying what's known as user data to an instance to actually boot that instance. And so it's largely a shell script that is usually created internally. And we were in that same place as an organization. We had a wide variety of different boot scripts that all sort of deviated from their various predecessors. And so the first thing that we started doing as we really focused on automation and standardization was to have a standard boot process based on the cloud init process that's baked into basically every AMI that you find, at least for the Linux world, and then there's a similar process for Windows. And the only goal of this first bootstrap process is to connect the instance that has been stood up to the second part of our standardized build process, which is the Puppet Master. We focus largely on these two technologies, CloudFormation and Puppet, but you can replace those in your mind with whatever your preferred tool is. If you like Terraform, or you're leveraging some of the newer tools that will create CloudFormation for you or just interact directly, or if you want to use something like Chef or Salt or Ansible. But the main point is that you have these two elements that help you take care of the entire lifetime of an instance. And then once you've got your instance attached to your configuration management server, in this case, as I said, for us, that's the Puppet Master, you can then start configuring those standard things that are the common elements across all instances deployed in a architecture. And at this point, we have a deployed instance that we can now use for ongoing software updates, deployment of custom software, whatever is needed for that particular instance. And we really are getting closer to that goal of disposable infrastructure because we've got a well-understood process for standing up an instance and a very regimented process for establishing the config scripts that we use to actually deploy these things that go on that particular instance. So simultaneous to this, we also have a process of checking it in this code to make it as easy as possible for engineers who want to change infrastructure to do so. So this is where we get into sort of the next element of constant change and again, you might see some of these things as familiar on the manual side. Again, we're still talking about human error. We're talking about there being a high risk of change, and we're talking about there being an increased amount of time to actually implement something. And then the fourth element that we're mentioning here, this idea of rollback being difficult or impossible. If you're making a major change to your infrastructure and you're touching a lot of different resources and modifying a number of different objects, it's critical that you have some sort of plan to roll back those changes that you made, because maybe after deployment, after going down that rabbit hole for a long time, you find that your whole premise of how you were going to architect an environment was incorrect. We need that ability to go back to that original state. And there's a lot of different ways that can be achieved, but in a manual approach, it's far more difficult to really achieve that in an effective way where we can be sure that after a failed deployment or a failed update, that we have this guaranteed knowledge that we can roll back to the previous state. So when we leverage an automated approach, we're changing code, not the actual servers themselves. So this means we have the opportunity to revert that code change that we made. Anyone who's familiar with, again, this software development lifecycle, this is sort of a common approach. Really, rather than treating security flaws or broken systems or whatever as a failed deployment, we can treat these things as bugs in the software. So we have the opportunity to roll back changes that were incorrect, but we also have the ability to track changes as they go forward, because these changes that we make are going to affect all or most of the instances in a deployment. It depends on the change we're making and so forth, but that's where we really are going to focus on things like a deployment pipeline and review process to ensure that these changes that are made by a development team are done properly, and that there's a back out strategy should those things not work out. But then finally, we end up in a scenario where every server that we've defined maintains an ideal configuration. If we terminate that server and rebuild, we know that only the things that are required for that particular server are going to be deployed on that instance, and also that any sort of unexpected items that we might encounter, it's easier for us to track down the origin of these changes. An example of how one might use a Git process for tracking the changes made to an infrastructure, when you've got a deploy process that works directly out of a set of infrastructure as code, you effectively create an audit log of all the changes made to an environment. Now, another common scenario is dealing with instance or component failure. It's one of the things you hear often about AWS is this idea that, quote, your instance can disappear at any time. Well, that's not entirely literally true, but it is always a scenario we have to plan for. Now, AWS gives us lots of different tools to achieve this, but it's all based on the idea of having your deployment across multiple availability zones, and it's not entirely different than what we had to deal previously with a more conventional system where we make sure that we have multiple instances or multiple servers deployed in geographically separate locations. But when it comes to actually dealing with a failure, the manual and the automated approaches can be quite different. In a manual approach, when something fails, maybe you've got an alert that notifies a human person to actually take action. But then what's actually involved in that process? This person is going to either need to rebuild a server, either maybe, hopefully, from some sort of AMI snapshot that we've taken, but it's more likely that they're going to be building it from scratch or using a script that maybe was written a while a while ago and hasn't been tested with the latest distribution that they're running on, or whatever the scenario is, we run into problems where there's a high potential for downtime. So if we take an automated approach, we have a lot of different ways to deal with failovers. We can fail over to another instance in an autoscaling group and allow for the autoscaling group to replace the instance that previously failed. We can do an automated deploy of the most recent code to that particular instance, so that if in the time between when an instance fails and it's replaced, if there's been changes pushed out to the rest of the cluster, when that new instance gets added back in a properly automated environment, it's going to get the correct version of the code deployed to that instance long before it even gets added back into the cluster of instances that is serving that application. Now, AWS already gives you a lot of tools for high availability, but it's not magic. The tools are there for you to architect around this, but it's important to understand that steps need to be taken both to implement an automatic scaling process, but more importantly, to continuously test it. Now, AWS gives you tools like availability zones, extremely high reliability for their virtual instances, built-in reliability with services like RDS. An RDS database instance is part of a back-end process that will automatically fail over to a secondary instance and take care of rewriting DNS records and all the elements that provide that data service. But when you're running your own EC2 instances, that's up to you to actually implement those items. And that's leveraging tools like either AWS autoscaling or more recently leveraging things like CloudWatch recovery, where a failed instance will automatically be restarted a certain number of times. But ultimately, it's your responsibility to implement this and to test it, because you're going to have scenarios where whether you're leveraging capacity planning and you have to plan for the addition or removal of instances, or if you're just trying to achieve self-healing, these things, again, are not automatic and need to be implemented. But then once we've actually achieved that, we've got a variety of opportunities for actually testing those things. And so this is where it really becomes important to leverage tools where you can empirically prove that your environment is resilient. You have to actually have, just like we would have disaster recovery game days and things like that, we have to have a process for establishing these test days for instances where we actually terminate an instance or whatever. But you can also use tools like, when you're really sure of yourself, like Netflix is, you can create a tool or use a tool like Chaos Monkey. So Netflix actually runs this across parts of their infrastructure on a regular basis, and it basically randomly terminates certain elements in their infrastructure and allows them to actively test their recovery process. By using a tool like this, it can expose unexpected failure scenarios, and it can also ensure that you've got a provably redundant and resilient environment. Now, finally, we get to ongoing deployment, and this is sometimes the one that most people really focus on, because I feel like we're used to the idea of developers making ongoing changes to a program or an application they've created, but it's less common for infrastructure engineers to think of that way. But at the same time, we still have to provide that sort of support that is required for this ongoing deployment. So we're looking at another scenario where we're comparing a manual approach where there's an extremely high risk of error, and this might entail, for different organizations, might entail SSHing out to an instance, dropping some files in place. There's both an opportunity for exploit across, we have to open up these instances to allow access to them, but also that same opportunity for human error to raise its head, that we forget to update a file, that we don't include all the changes that we expect to make, and this can cause further updates. So by taking an automated approach, this works us closer to things like having a push-button deploy process, or a Git-powered or Mercurial-powered process where after a commit is made to a certain branch, an automatic process goes and deploys that into your environment. But then this can be used for a lot of different things. We're increasingly using this as a method to deploy our actual cloud formation. So we're following that same software development lifecycle that we're used to from the old world, and we're applying that to the infrastructure we actually stand up. as organizations become more sophisticated and they start using tools like configuration management and containers, the same kind of process can be at play where a code change to a set of configuration details for an instance has to go through a linting or approval process before it actually gets deployed. With regards to containers, this is an area where, you know, I'd say it's pretty fair to say that anyone working with containers is already looking at an automated build chain for this, but then what you do when you're deploying a container is you're actually moving some of those challenges, some of those things that can fail, part of that responsibility for configuration management is shifted down a little lower in the stack down to the area where the developers can modify this themselves, but we still have to go through an automated process to confirm that those containers build properly, that they have all the necessary components installed, and that any sort of changes to them are adequately recorded within whether it's the Docker container or the instructions to create that container. Now here's an example set of pipelines that can sort of show the complexities that come into play when we're dealing with this is a process that describes standing up a new ECS cluster and running a series of Docker containers on it. This was actually is a variation on a process already used by one of our clients, where as part of their deployment process, they first use the AWS service catalog to deploy the actual cluster itself. Now, if anyone's not familiar with ECS or Docker containers, essentially an ECS cluster is a series of machines that will take care of placing the container that you're trying to deploy and ensure that any sort of load balancers or other connectivity is properly routed to those containers. But then once that cluster is up in this particular pipeline, another process can be kicked off on the GitLab server that is actually going to take the particular source code for that container, compile it into an image that can then be shipped to the Docker registry via Jenkins. So Jenkins takes care of any sort of communication with Docker and with the ECS service that we created in the first step. And this means that we now have a process for doing a complete deployment of an entire clustered application. So this can include a variety of different images, a variety of different Docker containers, but we can do all this through an automated process where we're using scripts and templates that have been vetted by a variety of engineers and also have been deployed in a variety of different environments and achieve a very regimented process for ongoing deployment. And honestly, this is talking about Docker, but you can deploy the same premise to any sort of software that you need to be able to update frequently. And the more you leverage an automated approach and the more you use things like infrastructure as code, the easier achieving a process like this is going to become. Now, disposable infrastructure is increasingly a large concept in the contemporary web world, and it's based around the idea that it's expensive and time-consuming and often boring to fix a server. We want to have a repeatable process for creating servers, and once we get far enough that we've created that concept, once we've gone far enough that we've created a script or a process that ensures that all these things are installed automatically, it's a really very short jump to leverage a truly disposable infrastructure. Why fix a server when you can throw it away and build a new one? So part of the premise of disposable infrastructure is the idea that the infrastructure you deploy, and in a lot of cases what we're really talking about here are either EC2 instances or Docker containers or VMs at some level or another, that these things never stray from an initial known good state. And you're forced to test the failure process, the more you're forced to test the failure process, the higher certainty you have that things are going to work properly during a failed event. This is, again, treating failure as a routine and continuous way of doing business because, again, we're planning for failure at every step in this process. However, we need a full automation of the process that's used to actually stand up that instance. So this is where leveraging tools like Docker can come into play because the thing that we're bringing up, the actual item that we're replacing, a container is far more lightweight than an actual instance that's deployed in a typical environment. So again, we're getting closer to this idea of dealing with failure as a routine event, and that at any time we need to, we can always destroy an improperly functioning element and replace it with something new. Now, as I mentioned, you can really apply this either to containers, which is the most popular scenario where we describe immutable architecture and is arguably the only true approach to immutable architecture in this environment. But you can really also just use some of the lessons learned from immutable architecture, even in a conventional EC2 deployment. And so here is a example case study from a company that's a client of Logicworks. They're an enterprise backup software company, and failure rates were an extremely important concept for them. They had a extremely detailed testing process that went through both automated and black box, one-person testing, but they still wanted to ensure that they had that they were taking things to the next level with regards to automation and immutable infrastructure. And so as part of this, we created a custom AWS environment with that CloudFormation template library that we've assembled over time. And we've created sort of multiple templates for all the different tiers of the environment that was going to be in play. And they actually have about 19 different test environments where they needed an identical copy of their application deployed. And as part of this, they wanted to be able to very trivially replace the last deployed version of this application on a very frequent basis. This environment, or any given test environment, can be terminated and rebuilt many times a day. So this is an organization that terminates something like, I think it's about 28 instances every 20-30 minutes. And so this is a lot of process that has to be constantly reiterated and rebuilt, and this approach is only possible with the idea of an entirely automated initialization process for this service. So, there's a question to ask yourself as to whether this is true immutable architecture or not, but it's certainly treated as if it were, because the entire deployment process for this company is to just terminate the old instances and allow them to be replaced. So then, in the end, by following this approach, they've been able to achieve an extremely low instance failure rate. Individual instances almost never fail for them, at least because of any sort of instance level issue, because they're constantly testing the process for replacing that. And so anytime a bug might occur in either the initialization code that Logicworks maintains, which is of course been tested far more thoroughly, or in the code that they actually write to install their application, this information could be discovered very quickly. It's not like they're waiting until the next time they deploy the app to production to find out these failures. This has resulted in them having a 100% uptime for their production application, and of course a very trivial process for deploying to production, which really just for them is a single-click deployment on their Jenkins cluster that goes out and terminates the old instances while the new set are building. But this leads to them having no residual impacts from previous failed or past tests. So anything that they write as part of their unit testing or black box testing process will never have any impact on the actual subsequent builds of these servers. And then finally, this has led to this particular department having a 60% higher deployment efficiency over similar projects at their company. So it's been a success at all levels by basically taking some of the lessons learned from immutable architecture and applying them to EC2. Now, the security impact of automation is one that is increasingly an important part of how we describe the value of our automation process, but was something that for a long time we treated as an intrinsic element of the automation process, that we were very cognizant of the fact that we had these increasingly large numbers of automated processes doing things for us that used to be, our responsibility. And so we sort of took that saved time and used it to reapply that to the consideration of security during this deployment process. But at the same time, just some of the basic elements of an automated process really do help us with regards to security. Again, dealing with that aspect of human error, because we have a standardized and controlled process for both builds and updates, and there's little to no human intervention involved in the environment at all. So by taking these approaches, we avoid the scenario of like forgetting to add a particular element, or someone who's so busy that they actually forget to add a particular security control that's a core part of keeping the system safe. That kind of stuff is always inevitably the first thing that we script, test, and implement. This also relates to patching. We have the same ability during a patch, which if we think about it is really just an update to our deployed infrastructure or to our deployed instances. We have the opportunity to patch from a central location, essentially. A great example of this would be something like on a Unix environment. I always refer to the fact that how many times have we had an OpenSSL vulnerability over the last couple of years? And so being able to say from a single location, ensure that all my instances are running a minimum version of this particular library, allows us to patch from a central location and have consistent versions deployed across all of our environments. And then because we're putting this as an element in our infrastructure as code, we're adding this to our manifest to ensure that a particular version of the software is deployed. It means that anytime we deploy that environment again, anytime we recreate that instance lifetime someplace else, we are already corrected by our configuration management system to the latest version of the library and the correct, non-vulnerable edition. Another thing that Logicworks really spends a lot of time on is the concept of background scanners, or automated agents that can crawl through the various environments that are under our management and apply certain security standards and notify us if those standards aren't met. This diagram here on the screen shows, a not terribly complicated environment. This is a very common set of things to see, a reasonable number of instances, not particularly large, but as you can see, there's a lot of complexities to how things might be routed across them, and different challenges here where there's a number of items that we may need to secure properly. In this case, we might be looking at making a change to the security group that protects the application tier, and maybe in the process of doing that, we wanted to lock it down, but we accidentally made it open to the world. By using some of the AWS API tools that are made available to us, our background scanners can find these kinds of issues, both in conjunction by doing direct scanning and also looking at some of the AWS services like Trusted Advisor. We can basically find that there's a configuration change that needs to be made, and report that back to our NOC, or even in some cases take the corrective action in place. This is something we do with some of the more crucial items, things like ensuring that CloudTrail or AWS config are enabled so that we can have a consistent audit log of the changes in an environment. When our scanners find that either those services are not enabled, they will proactively re-enable them for us. So this is a great process, a great thing to start looking at if you have an environment that is not entirely under your control. You can leverage some of these kinds of tools to ensure that failures and regressions don't happen at that time. Now, we've talked a lot throughout this about some of the tools that we use, but we've really only touched on some of the different ways in which you can use them. So the two major tools that make up our practice are CloudFormation and Puppet. And as I said, you can just as easily, in your mind, replace CloudFormation with one of its other tools like Terraform or Troposphere or what have you. And then similarly, you could easily replace Puppet with something like Chef or Ansible or whatever your preferred configuration management tool is. But the main point is that for each of these common security elements, we have a solution and a process for following an automated approach to these things. So whether it's ensuring that security groups follow a certain format or a certain set of standards for what kind of ports we open or not, anything about how you control the ingress and egress of the individual subnets within your environment via the network ACL, subnet sizing, and even just naming conventions, all these things can be kept in play and kept correct by CloudFormation. And so this is really core to any sort of AWS resources that we're going to deploy in an account. We're going to leverage CloudFormation to do so. But then, excuse me, once a EC2 instance is stood up, there's still more work to be done. There's things like tying the instance to a centralized authentication server, ensuring that the right antivirus is installed and that the latest definitions for viruses have been uploaded. If there's any sort of requirements for doing log shipping or ensuring that you're retaining logs, Puppet is a useful tool for getting that log shipping agent in play and adding additional logs to be shipped to wherever you need to have them. And also just standardizing on things like users, software versions, and other elements of any EC2 instance. So in summary, automation is great. You should definitely do it if you're not already. But the reality is that any step forward on this path is going to be useful to your team. You don't have to boil the ocean. You don't have to do all this stuff all at once. But we do think that if you really don't want to work if you're going to pick one area to focus on, I pretty much recommend that you start with configuration management, that you get to a point where when you stand up an EC2 instance, you have a standard process for deploying any of the elements you may need to install in place. But most importantly, if you don't want to worry about infrastructure and you'd like to focus on application level DevOps, you should contact Logicworks and we'll help you out. I think this is it for my talk here, but we'd like to open up for some questions, and I know that there's been you have the opportunity to send in additional questions via the GoToWebinar interface here. So we'll just start going through them here, and if we don't have an opportunity to get to your question on the call, we will be sending out responses afterwards, along with anyone who's looking for a copy of the presentation. We'll be sending that out to everyone who signed up, so we'll have that as well for you. Just pop this out here. All right, so one of the first questions that came up was about how to leverage this kind of work within existing VPCs. You know, it's definitely true that it's a challenge when you inherit an environment or if there's something already stood up. Fortunately, when it comes to CloudFormation, there's been a lot of improvements with regards to the features of CloudFormation itself that can help with things like leveraging existing VPCs. So the first challenge is usually just that you'll need to create a template that allows you to pass in the elements that you can't just retrieve by standing up an instance. So an example might be if we're used to standing up a VPC, when it comes to actually putting an instance in that VPC, we're going to need the identifier for that network that we created. So then one of the things we'll just do is we'll create a template that allows us to pass that information in. As CloudFormation has evolved, it now has some very nice options for doing things like validating that VPC ID that you passed in is a correct ID. It actually, will test to ensure that that VPC actually exists before you can even get past that parameter page. So really the key with CloudFormation on most things is it's sometimes a matter of climbing the mountain, because until you really get to the top, you kind of can't see all the different ways in which you can get around different issues. But this is true for any of the major tools that are involved with this, similarly like Terraform and so forth. Another question was, let's see here, how hard it is to learn Puppet. And honestly, it can be a challenge, and I think that it depends on your background and your approach and so forth, but I would say that for me, the key element was I started using Puppet just to do my software deployments. Prior to getting into infrastructure design and the cloud and so forth, I was a software developer for 15 years, but for whatever reason, it seemed like I never had anyone to help me do the actual deployment, and a lot of our deployments were manual and so forth. So I just selected Puppet somewhat on a whim, and so I don't necessarily recommend that to most people. I would say it's worth trying some of the various tools that are out there, and these days for people who are developers, I tend to suggest taking a look at Ansible first. If you're creating scripts that are based on the idea of I need to do this thing, Ansible is particularly good. It's a nice interface and it's got a lot of popularity. A lot of our reasons for choosing Puppet were based on the fact that we wanted to have something that was going to be continuously checking in, because it provides us with a way of monitoring the existing infrastructure that's deployed. But even when it comes to learning Puppet, we learn these things in stages. You know, we started with a very basic approach that didn't even use a Puppet master, that we just checked out a set of Puppet manifest and used Puppet apply to apply those scripts to that instance that was in place. But the real challenge with Puppet is getting a handle on the idea that you're really just specifying a map of dependencies. And for some people, it's a little more difficult to think in that method. Chef has a similar process. And so, you know, I think all these tools are extremely useful, and it's worth checking them out for yourself to figure out which one is the best for you. A quick question that came in here, and I think it's actually also related to the next one I was going to touch upon, is why we chose CloudFormation and not Terraform. And one of the things that I feel like comes up really often is that Terraform is focused on this idea of a multi-cloud approach, that you know, you can create a toolkit that can service all these different clouds effectively using the same basic language. And there's a lot of truth to that, but the other thing that we had to deal with as an organization, that maybe individual stakeholders may not really have the same requirements that we do, is as an MSP, it's important to us to select technologies that are going to be have the most support for our clients should they need to manage these environments on their own. You know, when you have an MSP, the account that they manage for you is still your account. So you always sort of want to know that should you want to take a different approach, that you're not going to lose anything in that sense. And so a lot of our choice to select CloudFormation was that there was just a lot more documentation available from AWS than there was specifically on Terraform, although that has changed quite a lot in the years since we made the selection. Increasingly, we are actually looking at Terraform. I would say some of the advantages is that I feel like Terraform fits into a CI/CD pipeline a little bit more effectively. On the other hand, CloudFormation is going to be updated for new AWS features far more quickly than Terraform will. Increasingly, it's still very competitive, but it's something to consider. So our choice was based largely on the size of the community around CloudFormation and the fact that we believe that whether you're deploying, a good example when you're thinking about trying to achieve cloud agnostic approaches is that one of the background lessons is always there's the idea of OpenStack and CloudFormation. OpenStack is essentially the same language as CloudFormation. It's the same JSON schema architecture, but at the same time, it's uses entirely different components. So even though these are effectively the same language, you can't take a CloudFormation script and use it on an OpenStack environment and vice versa. The same thing is true about Terraform. The same thing is true about any of these devices, is that you're largely going to have a different architecture on one cloud provider than another. Now that may change in the future, but at this time, it's something to consider, and it was certainly a requirement for us. One of let's see here. There's another question came up about the fact that we're using Puppet and asking if Logicworks uses any other services, and we do. And in fact, Puppet is usually in most of the environments that we interact with, but it doesn't mean it's the only configuration management tool. Oftentimes, we'll use Puppet to get the environment stood up in the first place, but one of the main things that we have to navigate with our clients is sort of a handoff between the elements of an EC2 instance that will stand up on their behalf and the items that they're going to take responsibility for, largely the actual deployment process of their custom software. So at that point, what it means is that it really doesn't matter to us if the client would like to use something like Ansible or Chef or what have you, because we can just invoke that at the end of our Puppet chain. As far as actually supporting these other tools, we support them in the sense that we'll make sure you have all the connectivity you need to install your own configuration management tools. We do think they're all perfectly valid choices for someone who's deploying an environment, and that it's really just the best way to achieve automation in your environment is to use the tools that your team is most familiar with. And so when we partner with a company, when we take on a customer, our goal is to keep as much of that stuff the same as we can. But the reality is always going to be that we have a lot more expertise in Puppet. We've done a lot more in it. We solved a lot of problems in it. And so sometimes it's going to be most efficient for us to take a Puppet solution as opposed to something else. But these are all things that we frequently work through with our clients, and as of yet, our choice of Puppet has never really been an issue in any of the environments we've built, because we can easily integrate with all the others. The last thing I just want to touch on, there was a really great question from Chris McConnell about Terraform and state file management. Some of the challenges when you come into a automated environment, we're using scripts and so forth, whether it's Terraform or CloudFormation or any alternatives, is there can be challenges with manual changes being made in the environment compared to the actual expectations of this deployment tool. So whether it's CloudFormation failing because it's expecting to be able to delete something that you already deleted, this is a not every resource in CloudFormation has this problem, but it's one of the more frustrating ones that I'll occasionally run to. That's not entirely different than a Terraform problem where a change has been made somewhere in the environment, and that change didn't get put into the state file that Terraform keeps and everything. I think in the end, we're actually dealing with a scenario where CloudFormation probably has its own state file as well that it just keeps plugged into the AWS managed side of things. But in the end, anytime you are using a combination of automated tooling and a manual approach at any level, you are potentially subject to problems, and that's honestly one of the biggest challenges that Logicworks has, because as I mentioned, the accounts that we manage still belong to our clients, and it's still our responsibility to let them achieve whatever it is they're trying to achieve in their particular environment. But sometimes there are things that we have to work out with particular customers in the sense of, please do not make X kind of changes to this because it makes management of this more often. And these are the things that I hope we'll see get revised as the cloud environment and the tools to use the cloud become more sophisticated and evolve in time. So I think that's it for questions. I just want to thank everybody for coming on and listening. And as I said, we'll be sending the deck out to everybody who signed up after the call. And we really appreciate you joining.